illustration shows particles spreading inside a disk workspace. So here they've spread one step. They might, for example, be magnetized particles inside a Petri dish pushed by an external magnetic field. The particles start on this green arc, and they're bounded by a red and a blue locators. The propagated particles are pushed in the direction of theta and are incident along the arc drawn in blue. Often particles cannot be controlled perfectly, and this is modeled by specifying the angular spread of plus and minus delta on either side of theta. This demonstration shows the maximum. So the maximum is right here, this dotted line, and the minimum particle spread into which the particles can be manipulated. So I'm going to step through this a couple times. Here it steps forward, and now it's raised to this green initialized spread. And then you can either minimize it by going to this point here, or maximize by going across the arc. We assume a global input such that particles start in an arc along the right side of the disk, and then the left-hand image shows the particle distribution in green as they propagate in the theta direction, and the final result is shown in blue. So here we'll propagate across the other side. Theta direction is shown by this red arrow, and then the particle distribution is shown by these circular sectors. And if I click on this show path, then it'll put a bunch of more incident parts on the start next step around. So I'm going to start again and run this through here. And so if I show all these paths here, we can step forward, and you can see we get spread on this side, and then I can spread myself out again, step forward, again pick a new direction to go, and it'll spread it out. So the arc length can be initialized from 0 to 2 pi radians. So I can initialize my distribution by spreading this forward and backwards. And any initial distribution can be steered to a minimum arc length of 4 delta and a maximum arc length of pi plus 2 delta. Once the arc length exceeds the minimum, it can never be reduced to less than 4 delta. Similarly, if the arc length is ever less than the maximum, it can never be increased to more than 2 plus 2 delta. Every propagation step can add no more than 2 delta to the arc length. So you see I'm at this green spot here. If I want to maximize that, I'm going to come here, and all I can add is 2 delta. If delta was bigger, I can get a much larger step. If delta is smaller, it goes down to 0, I can get nothing. And so I'll move through there, step that up. I can continue adding 2 delta as I go along here until I've almost maximized it here. And then one more step, I'll be able to maximize that. Similarly, I can decrease it each time by half of the distance from the start to the goal. So I can decrease it by half here. And if you watch what's happening, what I'm actually doing is I'm trying to reflect alongside this sector that I'm inside of. So I'm collecting everything, dividing my air in half, and then I can converge again and keep on going until I've divided my air in half. And so I'll asymptotically reach that minimum value. Never quite get there, but I will be able to decrease the air by half each step. And so this demonstration was inspired by a similar problem in polygonal workspaces by Lewis and O'Kane. A big thanks to my co-authors Daniel Bao and Tate Song for building this beautiful demonstration.